Hello everyone, my name is Mihai and I will present our work on quantifying users' visual attention during everyday mobile device interactions. This is joint work with Sander Staal, also from ETH Zurich, and Andreas from the University of Stuttgart. In this presentation, I will first introduce the concept of attention. Then I will explain why analyzing attention allocation on mobile devices is highly relevant and interesting. And lastly, I will clarify what we mean by quantification and what we actually measure. So let's begin with attention. The study of attention and its allocation has many benefits. It can help model user behavior, such as user engagement, attentiveness, alertness, or boredom. It is relevant to assessing user interruptibility or finding the opportune moment to deliver messages and notifications. Moreover, by modeling the user's visual attention, it is possible to reason about the future. For example, predict where users will look next. All these advancements bring us closer to the vision of attentive user interfaces, which are interfaces that adapt and respond to human attention. We talk about attention, but what is it? It turns out there is no common definition or understanding of attention. In general, it defines how we process information in our environment. A widely accepted characterization of attention distinguishes between covert and overt attention. Covert attention is concerned with one's mental focus without moving one's eyes. This requires carefully instrumented environments and stimuli. In contrast, overt attention, also known as visual attention, can directly be observed in terms of eye movements. In this presentation, whenever I talk about attention, I refer to visual attention. So why are mobile devices particularly relevant and interesting to study? Mobile devices are used by millions of people, at home, while commuting, waiting for a bus, with friends, and sometimes even when we shouldn't use them, for example while driving. Because of this, our usage patterns have changed significantly. It is well known that mobile interactions have become highly fragmented and can last as little as 4 seconds. Similar conclusions can be drawn by looking at task disruption and the barriers faced when doing tasks on mobiles that can hinder productivity. Moreover, smartphone overuse can have negative consequences leading to attention deficits or even mobile phone addiction. Besides research, companies also have an increasing interest to know what users do on their mobile devices. You might have noticed that both iOS from Apple and Android from Google offer features that quantify how much time people spend on their mobiles. These apps can show its users detailed analytics. For example, what are the most used applications or how many hours users have spent on their phone in a day or in a week. However, they only measure the amount of time the screen is on, which cannot capture the individual and fragmented nature of attention. What we are trying to identify is how to go from screen time to quantifying the highly dynamic nature of visual attention. In this paper, our contribution towards understanding and quantifying visual attention during everyday mobile device interactions is twofold. First, we present the Everyday Mobile Visual Attention dataset, which is a novel in the wild dataset. Second, we present the first quantitative evaluations of attention in situ without the need for any dedicated eye tracking equipment. Let's have a brief look at the dataset. EMVA is a rich dataset that contains videos recorded from the front-facing camera every time a user unlocked their device. Besides videos, it contains sensor data, for example from the accelerometer or gyroscope. It also contains usage logs, such as the application running in the foreground. Interaction events, such as touch events, when they happen, but not their position on the screen. And even location data, which we anonymize to place types. This data was collected using an Android application that ran in the background, recording participants during their everyday routine. Because of the extensive data collection, our app had several measures in place to protect the user's privacy. For example, users had to review their data before uploading it. No data was collected without the user's explicit consent. Here are a few video samples from the EMVA dataset. As you can see, it covers different people in different environments, both indoors and outdoors, or while doing a variety of activities. Here are only a few of the characteristics of our dataset. There are 32 participants, 20 male, 12 female. Their age ranged from 18 to 59, with an average close to 27 years old. These participants used their own devices for the study, which is important for the ecological validity of our findings. The study participants shared over 14,000 videos with us, on average 447 per participant. That amounts to around 470 hours of video data and associated metadata, or around 15 hours per participant on average. The data was collected over a period of 2 weeks. In this figure, you can see a histogram of the video and hence interaction duration. While the average video duration is about 2 minutes, many videos, around 24% of them, are less than 10 seconds long. This further supports the theory that mobile interactions are highly fragmented. Now that we have briefly discussed about the dataset, let's move to the quantitative evaluations of visual attention of mobile device users in situ. In the context of attentive user interfaces, understanding when, how often, or for how long users visually look at their mobile devices is key to several tasks in mobile human-computer interaction. One way to detect when users look at their mobile devices is through eye contact detection. We use a state-of-the-art deep learning pipeline for this task. However, details about this method are beyond the scope of this presentation. For more details, please check our paper on arXiv. In short, the method takes as input an image captured with the front-facing camera and predicts whether the user was looking at the screen or not. Using this method, we automatically label all the videos from the EMVA dataset with eye contact or no eye contact information. Here's a short preview. Having this information, how can we quantify visual attention, and what do we measure? From eye contact labels, we extracted several higher-level visual attention metrics. These metrics are for one video recording, which begins from the moment a device is unlocked until the device is locked back again or goes into standby. In this figure, green represents eye contact, red no eye contact. By looking at the green segments, we can extract the duration of sustained visual attention. By looking at the transitions from eye contact to no eye contact, we can capture shifts of attention either from the device to the surrounding environment or the other way around. For additional attention metrics, please refer to our paper. From the visual attention metrics, we present a number of interesting findings. The average duration of sustained visual attention was around 7 seconds. The duration of the first attention span, which is the first segment after unlocking the device, was around 11 seconds. In a video recording, which corresponds to an interaction session, there were, on average, 4 to 5 shifts of attention towards the environment. In around 61% of the videos, the primary attentional focus was on the device. In around 6% of the cases, the primary focus was on the environment. For the rest, the primary attentional focus is unknown. This happens because in more than 50% of the images from a certain video, no face can be detected. Besides general visual attention analytics, we also looked at diurnal patterns. Through our analysis, we could quantify the diminishing nature of attention over the course of a day, from around 9 seconds in the morning to around 6 seconds in the evening, which further decreases at night. While not particularly surprising, our work is the first to collect such measurements unobtrusively, in situ, and without any special purpose eye tracking equipment. We also analyzed visual attention across applications. The participants in our study used over 400 different applications during the weeks of the data collection. We clustered them by category as listed in the Google Play Store. The duration of sustained attention varies according to the application that was being used. The same holds for the number of attention shifts. For example, for the medical or education category, the duration of sustained attention is around 10 seconds. While using a weather app, the attention span was less than 5 seconds. In summary, eye contact detection is a powerful tool to analyze overt visual attention in situ. By using such an approach, we can collect rich insights into attentive behavior, including quantifiable metrics. We also confirm previous findings that visual attention in mobile HCI is highly fragmented. This underlines an urgent need to develop attentive user interfaces that actively manage and protect such a valuable resource as human attention. Visual attention is both user and context specific. Proxy methods, such as Apple Screen Time, while they can provide insights into mobile phone usage, they are limited and cannot fully nor accurately capture the fragmented and individual characteristics of attention. Last but not least, face detection in mobile interactive settings is highly challenging due to occlusions or partial visibility of the face and facial landmarks. In our analysis, we used a state-of-the-art face detector that was able to detect the face in about 62% of the images, or around 235 hours of video data out of the total 472. For the remaining, we do not know whether the face detector has failed or whether the user was indeed not present. And with this, I have concluded my talk. For additional details, please have a look at our paper, and also check out the EMVA dataset. Thank you.